also use this, that's fine. Okay, so first about the motivation, I think we've heard already a lot about sustainable agriculture today, so I will keep it rather short. So our goal is to monitor ions or pH in fluids, for example, in soil or groundwater. And one application could be smart farming, so that the farmer knows exactly where to use the fertilizer and which amount is needed. This would lead to higher yields, no groundwater contamination, and also the protection of biological diversity. But for this application, and also for many other applications, like in healthcare, for example, when you want to wear the sensors, there's still a need for inexpensive and miniaturized sensors. So to make this visible, I wanted to show you an example. So how accurate can one sensor in a big field be compared to a big sensor network in the field? So therefore, our goal is not to improve the sensitivity and the selectivity of the sensors, but our focus is more on decreasing the costs of the sensors, and this is often done by decreasing the size of them. So we are using a new sensing principle for potassium sensors. We're using a capacitive sensor design instead of a potentiometric sensor. We're here having a foil substrate, for example, a PET or a PEN foil. And so on this foil, we have interdigitated electrodes that are covered by the ion selective membrane. And I think we've heard it a lot today how it works. So we have the potassium ion foils inside of the membrane. And in our case, we then apply an AC signal, so a voltage across these electrodes from a frequency ranging from 1 megahertz to 100 millihertz. And we measure the impedance changes of the membrane instead of a potential shift. It is important to mention that the thickness of the membrane is a critical point. So the larger the electrode dimensions, the thicker the membrane needs to be, because we want all of the electric field distribution inside of the membrane and not inside of the electrolyte, because then we get a better selectivity and sensitivity of our sensor. So if we compare this to the state of the art, which are potentiometric sensors, the potentiometric sensors have a high sensitivity and high selectivity, but they require a reference electrode, which adds more material that is needed, and also is often prone to drift of the sensors. And it needs they often, like all of the papers I know, use a PVC membrane, which is not printable. So in our work, we don't need any reference electrode. Our sensors are fully printable, also the ion selective membrane, because we use a too accurate membrane. And by this, we can decrease the cost, and the sensors are also quite simple to miniaturize. So now I will compare two manufacturing methods of our sensors that we investigated. So the first one is printing of the sensor. We used inkjet printing, and we used the same printer as all, I guess. And we printed the silver electrodes first. Then we cured them to make them conductive using intense pulsed light, because our PET foil was very temperature dependent, so we couldn't heat the substrate. Then we printed the ion selective membrane on top and cured it via UV light. And you can see the results here. So we achieved quite good quality of the electrodes and good resolution of 90 micrometers. And the yellow thing here is actually the ion sensitive membrane. We had to print a lot of layers on top of each other, because the membrane, so one layer had only a thickness of a couple of 100 nanometers. So in order to achieve a sufficient thickness, we printed 6 layers on top of each other, but it took already like half an hour to 1 hour. So there was a need to switch the process, actually. So we tried another fabrication process, which is a mask process. And it's really simple. So you can use any kind of substrate. Here in this case, we used a PEN foil. We covered it with wafer tape that is like used in every CMOS process. And then we used a laser to structure the electrodes. And we removed only the inner part of the for the electrodes and sputtered 100 nanometer gold on top. And then we removed the rest of the wafer tape, and we got really good quality of the gold electrodes. The dimensions are slightly increased, so we now have 500 micrometers width and distance. And by drop casting the membrane, we could achieve a thickness of 10 micrometers, which is actually thick enough for this application. And now to compare these two methods, they both have their strengths and weaknesses. So with the mass process, we have an increase in the electrode dimensions, but we have the advantage of being able to use gold, which is biocompatible compared to silver. And the membrane thickness is increased by a factor of 10, which is actually advantageous for these electrode dimensions. It's also in inkjet printing. In inkjet printing, we could also see uneven surfaces because we had to print a lot of layers on top of each other that lead to accumulations. And these also add additional capacitive effects to our sensor response. So this decreased our sensor sensitivity. By drop casting, we had good membrane quality, and in the mask process, even though we have an increase in fabrication step, the fabrication time is actually reduced because we could, for example, in the sputtering process, it's not done one by one, but we could manufacture multiple sensors in one time at the same time. The cost of both fabrication processes are both pretty low. And I'm showing you the slide because I wanted to highlight that each fabrication process can be advantageous for depending on the application. So for example, if you want to prototype and make a lot of sensors to validate if they are working or not, we're actually using the mask process because the fabrication time of the electrodes is rather low. But for example, if we can decrease the electrode dimension by using a silicon chip, for example, then the membrane thickness of the inkjet printing would be sufficient, so we can take advantage of this method. Now, if we want to look at the sensor performance, we can see here we applied the frequency from 1 megahertz to 100 millihertz, and we can see with increasing ion concentration, the sensitivity of the impedance of the sensor decreased. At 100 millihertz, we actually achieved a good sensitivity, I would say. It's difficult to say because I cannot compare it because everybody else has potentiometric sensors and they use millivolts per ppm, for example. So we're using megaohm per millimolar per liter. The resolution is quite good, and the accuracy is okay, but I think for many applications, this accuracy is sufficient. Then we checked the cross-sensitivity towards sodium, and we achieved the best cross-sensitivity at frequencies of 100 millihertz. And by looking at the change in the real part of the admittance, and we can see by the steeper slope of the potassium ions that the sensor is more sensitive towards potassium compared to sodium. We also checked the sensor drift, and the sensor has very low drift. If we look at this value, it's less than 0.5% per hour, and this is even lower than the resolution of our measurement device. So it might also be due to the measurement device. And these peaks, actually, they stem from environmental noise because we're measuring such high impedances. We catch a lot of environmental noises. Then we also manufactured 4 different potassium sensors on 4 different days, and we measured them on different days. And the reproducibility is pretty good, especially at the very low frequencies again. So the error is less than 7%, which is similar to the accuracy of the sensor. And summarized, we can say that here we introduced a new membrane ink from Impedimetric Potassium detection. We introduced 2 simple and low-cost manufacturing methods, and the shown sensors showed a selective detection of potassium ions, low drift, and good reproducibility. And in the future, we want to conduct more cross-sensitivity tests. We want to make more sensors that can also detect pH, calcium, or magnesium. And we also want to bring the sensors on silicon. So here are our silicon electrodes, and we want to inkjet print the ion selective membrane on top of those. And that's it from my side. I want to thank my colleagues and my collaborators, and yeah, you for your attention.